So let's look at this example. We want to determine the shear force and the shear and the moment of this beam as a function of x. Now we have a different scenario here. This is the expression. We have our UDL of 50 kilonewton per meter, and our point load here to be 50 kilonewton, and our moment here is 50 kilonewton meter as well. So we want to get the function as want to get the shear force and the moment as a function of x. Now, how do we go about it? Let's make a cut or a segment here. Let's call this segment at this particular point of x1, and then see what we are going to have here. Now, if we make a cut of this segment at x1, what are we going to have here? The first thing is that this if we make a cut here, we consider our UDL, which is equal to convert this UDL to a point load to be this force times the distance is span, but the distance is x1 that we're considering because we are making the cut here. So 50 times x1, that's the point load acting here first, 50x1. And however, another important thing that we have not considered, because before we start making this cutting, we were told that we should first get the support reaction first. From there, we will know what to do. So to get the support reaction, we use this to get our support reaction. How do we get that? We have 50 kilonewton here, and we have another 50 times 2, which is 50 times 2. If you convert this one to point load, 50 times 2 to be acting around here at 1 meter solid. That's 100 at this point. Now we have 100 here, we have 50 here, so definitely the shear force at this particular point will be 100 plus 50, which is 150 at this particular point. That's the shear force. So now, how do we know the moment to this particular point? The moment is 50 times 3, that's 300 minus 50 times 50 times 3, that's 150, minus 50 times 2, that's that would be 50 times 2 is 100 at this point, times this distance 1 plus this 50. That was the moment here. I think I should put that one into writing. Let me just write it out. So 100, this one will be 100 here, 50 here, 100 plus 50, that's 150. The shear force, I said, is 150 at this particular point. Why is it 150? Because there's no support here, so it's 150 pointing upward. However, the moment is this moment to this particular point is 100 times 1, that's 100 plus 50 times 3, 150. Sorry. Plus 150, then we have a 50 kilonewton meter moment here, plus 50. So if I add 50 plus 150, that's 200 plus 100, that's 300. So that means the moment at this particular point is 300. Summation of these three will give us 300. So the moment here is 300 kilonewton meter. So now, since we already know that one, and we are considering this particular, that's the first thing I told you the first thing we calculate is the shear force and the moment. So we're supposed to calculate the shear the moment of that at that particular point first. So having known this moment and the shear force, now we can now consider it based on this expression of x, whatever it is. Now, if we make a segment to this particular point x here, now how is it going to be affected here? It will not be 50 times x for the shear force here, 50 times x1, which is what we have here. Now however, if you want to take moment to this particular point, it will not be this times this, it will not be a point load acting at this place times this distance. So we have to be very careful. This time around it will be this one times x1, that will make it a point load, times now x1 over 2, because it will make 50 times x1 will be here, times this x1 over 2 is very important. Because we have to take into consideration the effect of this particular moment to this section. So for this particular one now, let us look at it in this form. For this particular one, we have 50 times, okay, let's say when our x equals to 2, 50 times 2 is 100 here. Sorry. Okay. We already know, we have calculated this one already. We have calculated this one already. This this one is given, and this one is given already, and I think I've explained this one also. Okay, okay, let us look at this. Maybe when we are taking consideration of x2 here, if I want to make a cut at this x2, what happens at this s2? To calculate the shear force to this s2, we have it this way. The same thing as for shear force is just summation of forces along the x-axis and summation of forces along the y-axis. So for this one, we have 100 here, and if this one is this one will be 100. This one is 100. Sorry, this one is 150. So this one is 150. This one is 100, and what will I have again? This 100, this 150, this 50 here. If for the shear force is just straightforward, we have 50 times 2, which is 100, as I've calculated here. We have 50 here. 100 plus 50, that's 200, and 200 plus 50, that's what I say. 100 plus 50, 150. So we have 150 at this point here. Now let's consider, we are considering S2 now. If we make a cut here, at S2 here, to calculate the shear force, the shear force is still the same. The moment is what we might differ. This time around, the moment is 100 times this distance. Now, what is this distance? 1 plus, that's 2. But we are considering it as a distance of x2. So to now say, okay, from this distance from here to here, it equals to s2 minus this distance 1. S2 minus 1, that's this distance here, S2 minus 1, because we are using S2, we are not considering S1 now, we are using S2 to calculate our expression for this. Now, apart from that, there's no other thing. The shear force, which is 150 multiplied by x2, which is a straightforward something. If we want to put it now in writing, let us see the expression. Okay, let us look at the calculation. I said the support reactions, which is at fixed point, is 150. I believe we all know how we got this 150. I've explained already. The moment I've explained it to be 300, and since there is a discontinuity in the loading, that is at s equals to 2 meters, the two regions of s must be considered in order to describe the shear force and the moment for the entire beam. What do they mean? That is, we consider two segments from 0 to 2, and from 0 is less than or equal to x1, which is less than or equal to 2, and likewise for this particular case we will still continue for the next one. S1 is appropriate for the left 2 meter, and S2 can be used for the remaining segment. 0 is less than or equal to x1, which is less than or equal to 2 meters. Why can't we use S1 alone? Because S1 is the one that is treating uniformly distributed load, and this side, the uniformly distributed load, is not continuous, so we cannot continue to use S1. That's why we are considering the S1 for this particular segment alone, and why S2 is used for the remaining segments. So this expression is saying that 0 is less than or equal to S1, which is less than 2 meters. That is, for this S1, it only covers this range or this region. Now, summation of forces along S as it will be equal to 0. We can say, okay, what's the shear force here? 150 minus, what's the point load here? 50 times whatever it is, means 50 times x1 minus v equals to 0. That's the first expression. 150, that 150 is not debatable, because that's the calculation we arrived at in the beginning. 100 plus 50 is a 150. We can't change it. We can't just say because we are making the cut we only consider what is there. No, this normal central one is that we have to calculate the shear, the support reaction, and the support reaction here is 150, so we have to take into consideration. And the moment is 300 kilonewton meter, so we have to consider that when we do the calculation for the moment. However, to express the shear force based on x1 now, we can say, okay, summation of forces along the y-axis, that is both upward and downward forces. Now, summation of forces along the y-axis to be equals to 0, equals to 150. We continue. This one is a u there, but because this one is positive, this one is negative, minus 50 times x, whatever x1 we are cutting, 50 times x1. If we are cutting the x1 in any position, it will still cover 50 times x1. We can't just say 50. We can't say 150 minus 50, or sorry, we can't say 150 minus 100. Why? Because if we make a cut here, it will not be able to cover. So since we are using expression of x or function of x, it is times x. So whatever distance we are considering for s, it will still be applicable. Then 150 minus 50 x1, then minus whatever v it is, will give us 0. So when we take the v to be set of the formula, it will not be left. We will be left with 150 minus 50 x1, which is what we have here. That's the shear force expression. However, the moment is different. The moment is force times perpendicular distance. For this particular moment, we already know that the moment at this support is 300 kilonewton meter, so that one will be written out. However, what of for this particular shear force? This shear force at this point, if wherever we are making the cut to, this 150 times whatever maybe is x1 or whatever it is, we have to add that one. Please, this particular expression is for this. Let me say for this moment is for x1. Let me say when our x is cut to 0 to 2 meters, we can use it outside 2 meters for the first expression. So for this particular one, we have 300 minus this 150 x1. That's 150 x1. How do we get 150? I told you that the 150 x1 is the shear force 150 times x1. That's, but because it is the moment is coming this way, which is positive, but the shear force is coming this way, which is negative. That's why we're having minus 150 times x1. So this, we have taken consideration of this 150 and this 300 now. Now we are left with this uniformly distributed load. Now we can't just use 100 kilonewton for our uniformly distributed load, because it's a uniformly distributed load. We have to use it as a function of x. So how do we know what to use? It's equal to 50 minus 50 times x1. That 50 times x1 will first make it a point load, then times whatever distance we are considering, maybe x1 over 2. You understand? Times x1 over 2. That will turn into a moment. First times perpendicular distance. As I told you, if it is x1, this will be where the distance and the uniformly distributed load will be acting at this particular point. Then the distance is half of x1 we're considering. So that's why we have plus 50 times x1 over 2. Why is it positive? Because it is moving in this direction, which is anti-clockwise. Otherwise, see positive. Unlike this one that is negative. Now, is there another moment on this particular segment here? No. That's why we have plus m to be equal to 0. So we write this expression out. If we write this expression out, we have 300 minus 150. Sorry, m will not be equal to, let's say, 150 s1. This one 25 minus 25 s1 square, then minus 300. This is the expression. This expression is only applicable for 0 to 2 meters. 0 is less than or equal to s1 less than 2 meters. That's for this expression. Don't forget, please. So now, what if we are considering from this place to this place? So for that, we will now consider another equation for that again. Summation of forces along the y-axis will be equal to 0. This time around we have because we are moving from here to here, this one would have turned to a point load already on its own, because it's outside this point we are considering. We are not considering here now, we are considering from here to here. So if we are considering from here to here, then this one would have turned this one to a point load, which is 50 times 2, which is 100 acting here. So to know the shear force now, we have 150 minus 100 minus v equals to 0. Is there any other v around there? There's no other v. So we have 150 minus 100 minus v equals to 0. So our v is 50 here. Now for the moment, which is force times perpendicular distance, now we are considering from here to here. So all these other ones will be like a constant. So for the moment now, we have moment m, whatever moment we are considering, m plus this one is 100 times, what is the perpendicular distance? The perpendicular distance is s2 minus 2 meters. Sorry, s2 minus 1, s2 minus 1, because that this s2 comes from here, and this point load is acting at the center here, which is half of this distance 2. So it will be s2 minus 1, 100 times s2 minus 1 plus do we have another moment again? Plus, we consider this moment 300 minus this shear force. What this shear force? What is its own this shear force of 150 I think 150 kilonewton. What is its own calculation to that? 150 kilonewton is moving this direction, which is minus 150 times s2. 150 times s2 is this. So this for the shear force. This moment is this, and for the UDL here, this is the one covering for the UDL. So there's no other force along this moment again, along this point again. So we can, please, if there's any other, if it's not clear enough, kindly drop your comment on my what's it called? You can drop your question on my YouTube page, or you can ask me on my WhatsApp so that I can respond quick to your questions. So we already know how we got this one. I've explained that m plus this one is based on the UDL we have here, and this 300 is the one we have here, and this 150 is the for the shear force. So if we open this expression, 100 times s2 minus 100 plus 300 minus 150 s2. So 1 minus 150 s2 minus this will give us 50 s2, and 100 minus 300 minus 100, that's 200. So this 200, if you open this expression, this is what you're going to have if you open this expression. So you can differentiate, and you will still have the same thing by checking. You can, when s2 equals to 3 meters, and check what you have, whether you get the same result, and if it's not, let me know so that we can check again. So looking at another scenario, this one is when we have a slanting point load. So for this particular case, how do we resolve it? We resolve it to along the x and the y axis. As you can see here, we have to resolve any slanting load along the x and y component. So if we resolve this along the y component, we have 250 sin 60, and along the y it is 250 cos 60, like that. Then we can do the same calculation. It is very simple. You can try that, you get the same thing. So I want you to try this particular one and let me know what you come up with. I want you to check this. If there's a question on this, let me know. It's very, though, let me just give you a hint on how to treat that, because this one is 5 kilonewton per meter here, this one is 15 kilonewton. You can make a cut here and then break it into two. We have a rectangular and a triangular loading. So the rectangular logic is 5. So if you move 5 from here, you have 10. So the triangular logic will be 10 by 12 here. So you can use that for your expression. Half times base, half times 12 times 10. So that's what we have here. Half times 12 times 10. So you can always do that and check. And if there's any question, kindly let me know. This is it's a simple walkover. You don't need to. I don't need to stress myself on it. What else do I need to explain again? We have done all this one before. Okay. I think I will. If there's a question on this, if you don't understand this one, you can drop the question on my comment section so that I can still explain on it. I wish you wonderful time. Thank you.